So the ideas that I'm going to present here are really not my ideas. They're ideas that have been proposed by pretty famous engineers in the industry and have been widely adopted into the industry. These ideas are really about how to avoid fragile and rigid code, and code that feels like every time you touch it, something breaks, or try to implement a new feature and something else breaks. I can call that the ripple effect. Or maybe have a design that has kind of a hidden problem that stays hidden for a long time. So you commit an entire application to a design, and then years later you want to implement a new feature, and it feels like the entire architecture of the whole system is working against implementing that feature. This is why architecture is different than learning something else, like a new framework or a new library. Architecture is not something that you can just Google your way to success, because you need to know it up front before you even start writing any of the code. Architecture evolves. Something that Robert Martin, or Uncle Bob, has said a lot. Architecture defers decisions, such that you can make the decision later and later, the better your architecture is. And the later you defer a decision, the more information you have in order to make a better or the best decision. And architecture can help you in a lot of ways, from usability, maintainability, scalability, availability, extensibility, reliability, reusability, portability, and security. Those are all metrics in which we strive for the best and sometimes sacrifice one to get another without realizing what the true trade-off was. Design and architecture can really highlight those trade-offs and most of the time give you the best of both worlds. So what I'd like to start with are my two favorite definitions of abstraction. The reason I want to start with abstraction is because it's really the keystone of design and architecture. The first definition, this comes right out of a Robert Martin talk, and it is control flow versus dependency direction. So here in a direct dependency, you'll notice that control flow and the direction of the dependency point in the same direction. Now, if you were to introduce a contract, say an interface in this example, you'll notice control flow is unaffected. However, the direction of the dependency is inverted. Now, it doesn't have to be an interface. It can be, say, at a function level, it could be a delegate, or you could have overrides of base classes or dynamic code that has two dynamic objects that has the same methods and properties, for instance, so you could swap. The point is that you can now, say for controller that has a loose dependency on repository, you could swap out the repository for another repository, or it could be an entire composition of repositories that talks to not necessarily SQL adapter. It could talk to SQL and Mongo and a service. You could make all sorts of changes without controller ever knowing the difference. You don't have to change any code in controller. This is part of the power of abstraction. We'll get into more advantages a little bit later. Second definition of abstraction that I've liked from presentations in the past is declarative. And so to understand declarative code, it's best to understand declarative code versus imperative code. Imperative code says very specifically how to do something. Now, declarative code simply says what to do. It does not say how to do it. So in this imperative example, you have a user administration class, and in the save method, it knows how to validate the user, and it knows how to save the user specifically to SQL. So it knows all the details of both of those concerns. Now, if we're to abstract that and make it declarative, say we extract the storage of the user. Now user administration imperatively knows how to validate the user. So that's its single purpose. And then it says to save the user. It has no idea how the user is saved. It doesn't know if it's going out to SQL, out to Mongo, to some web services, or composition of storage devices. It has no idea how, and it doesn't care. So that can all change without user administration changing. You could think of these abstractions and not having to change things as kind of being a saving point in a video game where you don't have to go back and repeat an entire level. It works the same way in code. So next, I'm briefly going to get into design patterns. In fact, I'm hardly going to get into this at all. I more or less just want to make everyone aware of design patterns and that they're something that are worth studying and trying to use. Just being familiar with what they are and how they work can be extremely insightful into your own designs later. So if you Google these, it'd be well worth your time. Now, the solid principles are even more important. 3 out of 5 of these come from Robert Martin as well. And then you also have Barbara Liskov and Bertrand Meyer. Now, the solid principles, I think, have been widely misunderstood. A lot of people don't like some of these principles. And when I've seen that happen, it's usually because of a misunderstanding of one or more of the principles. And the people that seem to understand it more have more of a, as they're learning these principles, they're more about reflecting on a design that didn't work. And when they look at that design and why it didn't work, try to look at the solid principles or the dry principle or the damp principle, which I'll get into in a minute, and decide which of those principles or multiple principles did you violate. And as you become more familiar with how you violated these principles, I think that's when you really see the value of these principles, and that's when you can teach yourself how to best observe these principles in your design. So, and again, I'm not really going to go into these because, like I said, these are something that you really need to experience, so you can't learn them in a talk. Firstly, you have the single responsibility principle that says your code, no matter what level we're talking about, whether it be a method or a class or whatever, it should have one reason to exist and therefore should have one reason to change. Open close principle, which means your code is open for extension and closed for modification. So you should be able to inject behavior or wrap behavior around your code in such a way that when you want to change it, you can actually just inject the changed behavior, for example. You shouldn't have to change other code. You should be able to change the observed behavior of the code by injecting new code without actually changing the original code. There's probably a better way to explain that, but I think you get the gist. Liskov substitution principle. Now, a class should be substitutable for one of its base classes, is basically what that means. Now, interface segregation principle is, I kind of like to think of that as single responsibility, but for the interface. So single responsibility is just that, single responsibility about the implementation. Interface segregation principle is also single responsibility for the contract. And then the dependency inversion principle, that you should depend on abstractions instead of implementations. And in a lot of ways, all these principles are really all saying the same thing. They're all saying declarative code. They're all saying that you should use an abstraction, basically. And so I'm kind of going from the low level to the high level, design and architecture. So at a higher level, looking at hexagonal architecture, that's what I'm going to get into in the next slide. Hexagonal architecture has other names like onion architecture, clean architecture, ports and adapters, N-tier. It's got a lot of names, and for the most part, these are all pretty much describing the same thing, which is basically this. They have an edge or a very superficial layer where you have typically you have your frameworks and all of the very superficial concerns. All the logic that is at this layer should be logic that absolutely needs to be at that layer because it directly deals with the mapping to the entities or DTOs that communicate out over that layer. Next layer inside is your domain. This should be the layer that contains all of your business rule logic, and then next you have your core, and the core should feel like an extension of the language itself. Like you should be able to use your core in almost any other project. For the most part, your core might be a little bit tailored to the domain, but still doesn't have any knowledge of the domain, which brings me to my next point, that if you notice the direction of the dependency, they all face inward. They should never, ever face outward, and they shouldn't even point side to side. Now, if you look at flow control, it starts at the entry point, and it can go wherever from there, and eventually traverses and returns a response to whatever the entry point was in a typical system. So this is a general idea of hexagonal architecture. Now, if you were to zoom into this and kind of flatten the lines, this is a single use case, a single simple use case example of hexagonal architecture that I did in a Tetris game. This is looking at the back end of a user score leaderboard. And so you can see out of the web layer, I've got a controller, and then an interactor that I'm calling it, which is basically the declarative logic and kind of some mapping out to the web models, and the domain, which actually that contains most of the declarative logic. There's an abstraction in between those layers, and you don't always have that abstraction into the core. I think it's most important to abstract away from behavior, but if the thing that you're depending on doesn't have any behavior, if it is only data structure, or if it's very simple things like little extension methods that, again, just feel like an extension of the language, I think that's okay, as long as there's not much logic in those methods. That's okay to have a direct dependency, because things like extension methods, they still have their place. They're still very useful. You just want to be careful when and how you use them. Now, you'll notice in this slide at the bottom, I'm asking if you can spot the mistake, because there is a solid violation that is expressed in this diagram. Now, the mistake was, as you can see, in-memory leaderboard updater there in the domain. It does validation, and it's also updating the leaderboard. So it has storage and validation as two concerns. So in a refactor, what I did is put storage out at the edge, which is where it belongs. It was an easy mistake to make because I was just dealing with in-memory storage, which really doesn't feel like storage, but it still is. I should be able to swap in-memory storage for SQL storage or Mongo or anything else, and the leaderboard updater shouldn't know anything about it. But if I wanted to do that and it was all the same, then I might end up messing up my validation, because that concern was also in leaderboard updater. So that's why I extracted the in-memory storage as its own superficial concern that doesn't belong in the domain. And sometimes you'll want to separate concerns that are in the same layer. In fact, if you generally if you have a named concern, it should be a segregated concern. That's not always the case. I'm always adjusting the granularity of what my isolated concerns are in any part of the system. And that's just a practice that you get better and better at over time. So, test-driven development. This is by far the most important concept, in my opinion. So I'll just get right down into what it is, according to both Kent Beck and Robert Martin. Kent Beck is kind of the guy that he says that he didn't invent TDD. He kind of reinvented it because it was kind of an old practice. It didn't have a name, and it's a practice that just kind of died off as computers got newer and more sophisticated, and the development life cycle became a lot shorter because you don't have to deal with tapes and cards and all these other things and compiling that takes a whole day or anything like that. Anyway, he kind of reintroduced this long lost practice and formalized it as TDD, and we've noticed all sorts of advantages with it. But anyway, the 3 laws of TDD are: you cannot write any production code until you have a failing test. Second law, you cannot write any more of a test than is sufficient to fail. Not compiling is failing. You cannot write any more. Third law is you cannot write any more production code than is necessary to pass the failing test. So you're constantly writing a little bit of requirement in the form of a test, just a little bit of a requirement, and then writing just enough code to pass that requirement. So the requirement is always one very small step ahead of the implementation. And when you do this, it creates a very tight cast and mold symmetry between your test and the production code, and that's very powerful for design, because when you have that, you have to account for every single dependency, and you know exactly what the responsibility is of each dependency and how that dependency interacts with everything else. So oftentimes solid principle violations will be a lot more obvious in the test before it's obvious in your design, in your implementation. And you can change things, change your code, and if anything breaks, you should have a failing test that says specifically what broke and how it broke and why it's wrong. So you should be able to refactor your code all the time, and your code should just naturally be cleaner and loosely coupled anyway, because in order to test something, you have to abstract its dependencies, so you get a much looser coupled system anyway. But then when you can refactor with complete confidence, your code becomes even cleaner, because if you can refactor, run your tests, and see everything's fine, then you don't have any fear of the code. Now, it also helps you form kind of the shapes of your abstractions, so it can help you. It can either kind of suggest a design pattern that you know, or it can suggest kind of your own design pattern, which might be a composition of other design patterns, or a specific design pattern, only a little bit different, that's kind of custom tailored to the problem that you have. So TDD is very good at making you think about the dependencies and how they all work together. So in a nutshell, that's TDD. So if you remember this slide, say for example that I want to test drive the leaderboard updater right here. So if I want to test drive the leaderboard updater, that might look something like this, where you can see I've got the test here and a stub for the storage, because I know that the correct behavior will be calling into the storage under certain conditions, or that it should not call the storage if it's, for instance, invalid. But basically you can see that I'm swapping out all of the web layer from calling the leaderboard updater, and I've got leaderboard tests calling the leaderboard updater, and injecting that stub so it can assert that the iStorage stub was called when something should be stored, or was not called when it should not be stored. It also can run tests that it throws the correct validation exception for certain scenarios. So that's generally how I would test drive leaderboard updater in this example. Now, there's different types of code that feel very different to test drive. I've put them into kind of 4 different groups. We've already talked about what declarative and imperative code is. There's also the concept of pure and impure. Impure code is something that can fail or something that requires mutation. So say like a database update or updating the DOM in your UI, talking to a web service. And those are all things that can either fail or require mutation or both. In other words, side effects. And so that's what impure code is. Pure code is where the output of something is purely based on the inputs. So like a function that adds 2 integers. It doesn't do anything to the inputs. It doesn't mutate those inputs. And its output is only based on those 2 inputs. There's nothing in there that can fail. It's not waiting on any asynchronous operations or anything like that. Nothing is going out over the wire. There's no mutation. There's no side effects. It's pure code. Now that feels very different to test than something that is impure. Now out at the edge, you'll have imperative and impure code. So say like an MVC controller that returns a whole bunch of HTML, and because it's just going to change that view, and also it's talking to services and other things that can fail. Now, test driving this layer can be very difficult because your assertions are probably going to be on what the HTML output is. So either your tests need to actually understand HTML and CSS, because maybe it's outputting the correct HTML, but the CSS says that something is not visible, and you asserted that it was in the HTML, assuming that it would be visible if it's in the HTML. So the test assertions can be very open-ended and misleading. Running the test can be very hard because maybe you have to set up your SQL server and get the scenario just right. Dealing with authentication, setting up a whole network of things. And setting up the tests can be hard. Like I was talking about, setting up the scenario in your database and cleaning out those scenarios in between tests. So the cost benefit of testing this outside layer is really inverted, which is one of the many reasons that it's a good idea to try to keep this layer as thin as possible. This layer should really just feel like configuration of your frameworks and not much else, because everything else should be abstracted into the next layer, which is declarative impure. So this is code that has side effects, but those side effects have all been abstracted away such that they are testable. And if it's abstracted away, you don't need the web server up and running, because say like you're just calling into a controller that is just a class at that point. Your test can call into that controller and test everything else that's been abstracted out of that controller without actually running in a web server, for instance. So all of those concerns have been abstracted out. It's still impure because you had to write stubs that say that it updated the user or something like that. But anyway, you still have that declarative abstraction that allows you to test without having to set up a whole bunch of things. And your assertions are a lot more straightforward because you're asserting that something was called or something very simple and structured was returned. And if you have that structure, then your assertions can be very accurate and you aren't assuming anything. So declarative pure and imperative pure really feel the same way. It's just pure code. So you're basically asserting like a test that says add 2 plus 3 equals 5. Pure code, it doesn't get any more simple to test drive pure code. Yeah, you just have to try it. It's very easy. Now, a lot of times people see layered circles. A lot of people might assume that like, oh, you're only ever going to have imperative impure code out here at the edge. You can actually have all 4 types out here at the edge. You could think of this as having rings in a tree. You can have as many rings as you want. Now, while it's perfectly valid to have all 4 types of code out at the edge, I don't think you should ever have imperative impure code in your core. So the outer edge here kind of disappears as you go into your hexagonal architecture. Your core should be pretty much all pure code. Maybe in certain scenarios that I can't even think of right now, you can have some declarative impure in your core, but I kind of doubt it. So these layers kind of disappear as you go into the core of your architecture, but you can certainly have all 4 types of code as you go out to this outside layer. So at this point, I would open it up to questions. Thank you.